Well, hi everyone. Good morning or good afternoon, depending on where you are right now. Thank you for being here today. In this symposium, we are going to talk about number transcoding. So we're talking about how we convert from one notation to another when dealing with whole numbers and fractions. I'm Bella Starling-Alves. I organized this symposium with Ed Herbert, who's also here. And today we're going to have 3 presentations followed by a discussion. So first, Professor Dror, who is a PI at the Mathematical Linking Lab, will be presenting some data about how people write numbers in languages where we have some inversion. So when we first pronounce the units and then the other numbers. Then Malu Gomides, who is now a postdoc in Ireland. She will also present some data about errors in number writing. And then I'll be talking a little bit about fraction writing. And then finally, Júlia Silva, who is a professor at UFMG in Brazil. She's a PI in the Developmental Neuropsychology Lab. We'll make a discussion of all the presentations. So I'll invite George to start when he's ready. And thank you so much. It's nice to see you all here.
Thank you, Bella. Oh, wait. Okay. Got my screen?
Yes.
Okay. Thank you, everybody, and I'll talk today about this study that we did with Julia Van Murel and Hanin Kasimasawa and Rebecca Schweitzig. Did I say the name correctly? Okay. Julia, please interfere in the middle when I say to say the German words.
Will do.
Because we will be talking about Arabic and German and how they write numbers. And basically, we know that in English, we write numbers from left to right, and we also say the words this way. So we say 30, 34. But in Arabic and German, the order of writing and of saying the words is different. With the same number, we would say in German
34.
Thank you. And in Arabic, we would say Alba wa Thalathun. So first the unit words and then the decades word. And the question is how people write it. So when people write number to dictation, would they write the number this way? Also, as they heard it, starting with the first word that they heard, first to last word, or will they write from left to right as we write in English? And there are actually a few studies that examined this question. And the answer is, of course, that there is no single fixed answer. Writing first the unit and then the decade is quite frequent, but definitely doesn't happen 100% of the time. So in this study, it happened almost 50% of the times. It's also affected by education. The higher the education, the higher the chance to write from left to right. That is to invert the digits relative to what you hear. And it also depends on the specific type of the number. Sorry. So numbers that have single words, like these numbers, whole decades, which is 30 in Arabic, or tin numbers, which are 13.
13.
Okay, thank you. I got this one right. So in these numbers, we see the writing of unit decade. Decade is more rare. And when the number contains 2 words, the unit then decade writing is more frequent. But the question is, why does this happen? Why do people invert the numbers? Invert or not invert and why do why doesn't it happen all the time? Why does there seem to be some variability in this behavior? And we tried to think about it. We came up with a few possible answers to this question. One is this is just a matter of habits. Some people may have the habit of writing first the unit and others first the decade, and it could be a matter of personal choice. And if this is right, we should expect more UD writing, that unit then decade, in languages that are written from right to left, like Arabic, as the reading direction might affect the habits. A second possibility is concerns the syntactic structure of numbers. So this inversion of the words may require processing the number as a whole, processing its syntactic structure, and this might be difficult. And if this is the case, we should expect more writing of unit first, that is more failures to apply the inversions when the number is more syntactically complicated. And the third possibility is working memory, that this operation of inverting the 2 digits relative to what you hear requires some working memory resources. And if this is true, we should expect more UD writing, again, failure to apply the inversions, if the person has lower working memory capacity. And we basically set to examine these 3 hypotheses. So in this study, there were 82 German speakers and 44 Arabic speakers. We're still collecting data from the Arabic sample. So I'm going to show you only the data we have so far. And each of them wrote to dictation 100 numbers between 2 and 5 digits. They wrote it on paper. And we examined which numbers they wrote, in which cases they wrote first the decade or first the unit. We looked only at the correct answer. There was a low rate of errors and we excluded them. The stimuli were 2 to 5 digits, as I said, 25 of each length. And in 5-digit numbers, note that there are 2 potentials to inversions because both the decade and the units and the thousands and the 10,000s are inverted. So in Arabic or German, this number would be said as 3 and 20,000, 400 and 6 and 50. So overall, it means that there are 125 decade unit pairs. Most of them were numbers with 2 words, but there was also a small number of T numbers of around decades, a single decade word or a single unit word. So first, let's look at the effect of habits or strategies, which concerns mainly the comparison between languages. So here you see the overall UD, unit first writing rate in the 2 samples. You can clearly see that it happened in both samples and much more frequently in Arabic than in Germans. In Arabic, we reached 36%, I think this is, and in German, much lower. And you can also see that there is large individual variability here. So in German, almost about 80% of the people almost never did fail to apply the inversion. Most of them just wrote from left to right. And this looks definitely like an effect of language, which might indicate that it's a matter of habit or strategies that may depend on the reading direction. The second issue is the effect of number syntax. So does the syntactic complexity of the number affect the inversion? So first of all, let's look at the different types of number. Here on the left, you see the numbers that had 2 words. And here on the right, you see 3 sets of numbers that had a single word. This only decade or only decades here or only units here. Oh, you don't see my pointer. Now do you see my pointer? Okay, so
yes.
Because I was pointing at the other screen. Only decades here or only units here. We have very low rate a very high rate of writing to left, a very low rate of unit first writing. And in the teen numbers, which are typically considered as a single word, at least from neuropsychological studies, they're considered as single words. Still, we see here a higher rate of unit first writing. So this might suggest that maybe they're not 100% represented as single words. Maybe there is some decomposition there. And in the two-word numbers, the very high rate of first writing. Here in the middle, what you see is those people, the people from the German sample, excluding those who never inverted at all, who never wrote unit first. So we can see the effects more clearly. But there's another, so we definitely see the effect of syntax, a bit basically, because this is about the number of words. And another aspect of syntax is something very specific to Arabic. So if we look at 5-digit numbers, the syntactic structure of this number is pretty much the same in Arabic, German, and in English. We say basically the first triplet, and then the word 1,000, and then the second, the number of the second triplet. Right? So this is 65, the word 1,000, and the remaining one is the same thing in Arabic. Hamza was sitin, which is 65, and then alf, 1,000, and the rest of the number. But in 4-digit numbers, the structure is different. In English and in German, we still have a structure similar to the 5 digits. Single unit, the unit word, 1,000, and then the 3-digit number. But in Arabic, it's different. In Arabic, we say the thousands word connects with the word 1,000. So in this case, hamstalaf is a single word that means 5,000. And then we say the rest of the number. And we have some evidence from other studies indicating that these 4-digit numbers are processed as a single chunk. So in a way, these numbers are more syntactically complex because we here have a 4-digit chunk and also an irregular structure. And what we see here is that in Arabic, in the red bars, you see more unit first writing in these 4-digit numbers, definitely more than the 3-digit numbers, also more than the 5-digit numbers. So it doesn't look like the trivial effect of longer numbers are harder, but really an effect of syntactic complexity. And interestingly, and in line with this prediction, in German, this doesn't happen. In German, we see that 4-digit numbers are slightly more difficult, maybe. So more unit first writing than the 3-digit numbers, but there's no difference when we go to the 5-digit numbers. Also, the length effect that you see slightly, you see it mainly in German, slightly here, in Arabic even less. It's a very minor. Definitely, this is not the major factor that affects the unit first writing. We should also say here that the syntactic effect exists, but it's not huge, right? It's not even close to the effect of habits or strategies that we saw earlier. So we see an effect of syntax. Last thing is the working memory. Is the unit first writing more frequent in individuals with low working memory capacity? So in German, we see that it seems to be the case. Most people don't write always from left to right, but if we look only at those guys that are a bit higher, with a higher rate of unit first writing, there seems to be here an effect. Whoops, sorry. An effect of working memory. The people with lower working memory capacity measured here digit span do more frequently the unit first writing. But in Arabic, we don't see this effect. So there could be two explanations. Either the working memory for some reason has an effect in German and not in Arabic, or another possibility is that in Arabic, the other factors that affect unit first writing, like the habits, are so strong that they just mask any working memory effect. So we think that our data cannot really arbitrate between these two possibilities. But we do see the working memory effect in German. So basically, these are the conclusions, three things I told you about. All three factors seem to affect the way people write. Definitely the habits, strategies, which is has the strongest effect, and also a weaker effect for the number, syntactic structure of the number and working memory. It could be, there are many things still open here. The working memory effect in Arabic, it's not really clear whether it exists or not. And it seemed that this design we chose is not the best method to look into this specific question. Also, whether would the effect exists for syntactically complex numbers. We saw the effect, but we saw that it's relatively small. It was just getting near significance in our data. So we're in the middle of the data collection, as I said. We'll hope the results will get better, but this is definitely still something to look more deeply into. And of course, why exactly does the syntactic structure has an effect, if indeed it has an effect? For example, it's possible that processing the syntax requires working memory, and eventually it's all about working memory. And an important question also is, how should we teach children to write numbers? There are teachers, both in Arab-speaking countries and in Germany, who require children to write the numbers from left to right, which is hard. And it's a question of whether this is the right way to go. We can definitely think of advantages or disadvantages. We can hypothesize such advantages or disadvantages, but hopefully if we understand what is the precise cognitive impact of this, we can give a better answer to this question. So thank you very much, everyone, and especially to Hanin and to Rebecca, who run these studies, and of course to Júlia and Hans-Christoph. And thank you everybody for listening.
Thank you so much. We have time for maybe one question. So I will invite Malu to start her presentation.
I'm going to share my screen. Can you see it?
Yes.
Yes.
But it's not in the presentation mode, Malu.
Really?
Yeah, I think you shared like not the screen, but the window.
Okay, let's try again. Did it work? Okay. So hello, everyone. My name is Mariuche Gomides, aka Malu. I am a postdoctoral researcher at the University College Dublin, and I'm very glad to be here today. So today I'm going to present the paper, The Impact of Phonological Processing on Number Transcoding. I must say that this study is part of a collaborative project with researchers from Loughborough University and Federal University of Minas Gerais. So in this study, we investigated number transcoding, which is the ability to convert one numerical representation into another. number transcoding is a major building block for children's numerical development, and it predicts later numerical development. So it's fundamental to investigate the cognitive mechanisms involved in number transcoding. A prominent model that aims at addressing the cognitive mechanisms underlying number transcoding is the ADAPT model. To briefly try to explain this model, we could make an analogy with the dual-bolt model of word spelling. So the ADAPT assumes that in the first step of number transcoding, this verbal input would be phonological encoded. Then numbers could be transcoded, directly transcoded by retrieving their digit Arabic form from long-term memory, or be transcoded procedurally by implementing a series of algorithms. So we have basically a lexical route for number transcoding and a procedural rule for number transcoding. Oops. Okay. Another interesting aspect of the adaptive model is that it explicitly recognizes the role of working memory in number transcoding. So working memory would be important for the retention and manipulation of information during the transcoding processing, especially the creation of mental slots that will be filled out by the digit form of the number. Indeed, several studies have shown that working memory is a predictor of number transcoding. However, based on the components of the ADAPT model, we can assume that other cognitive mechanisms would be important for number transcoding as well. So, for instance, as I mentioned, the model assumes that in this first step, numbers would be phonologically encoded, and the authors argues that the phonological similarity of numbers will be detrimental in this first step. So we can hypothesize that phonemic awareness would play a role on number transcoding. Indeed, previous research from Lopes-Silva and colleagues show that phonemic awareness is a specific predictor of number transcoding, even controlling for the effects of phonological and visuospatial working memory. Since the model also assumes that there is a search in long-term memory and that in some cases numbers might be directly retrieved, we can also hypothesize that lexical access might also play a role in number transcoding. However, the contribution of this mechanism of the lexical access has not been investigated so far. Another very interesting aspect of the ADAPT model is that it assumes that different mechanisms would explain the errors present in number transcoding. So we know that error types in number transcoding are very systematic, and we can classify the errors in basically two categories, lexical and syntactic errors. So lexical errors, the lexical primitive, one number is replaced by another without affect the place value structure of the number. On the other hand, syntactic errors, these lexical primitives are retrieved correctly, but there is a change in the place value structure of the number. So basically, lexical errors would occur due to problems in this lexical root, and syntactic errors would occur due to problems in this procedural route. So, in this present study, we aim at investigating if lexical access specifically contributes to number transcoding. And an additional goal is to investigate if the three components of phonological processing, so phonemic awareness, working memory, and lexical access, are differently associated with the error types. So if we assume that these cognitive mechanisms are important for different components of the transcoding process, they might also be differently associated with these specific error types. In order to do that, we assessed 357 children with an average age of 8.82 years old from 2 different cities in Brazil. We measured their nonverbal reasoning and word spelling, which were used as control variables in the regression models. But we also assess phonemic awareness, working memory, phonological and visual-spatial working memory, and lexical access. So to answer our first question, we conducted hierarchical regression models. And the final model showed that visual-spatial working memory and phonemic awareness were significant predictors of the number transcoding. This partially replicates the results from the previous study from Lopes-Silva and colleagues that I mentioned. We did not find that phonological working memory was a significant predictor of number transcoding in the present study. And we hypothesized that this might happen because we used a more complex number transcoding task. In a second model, we include the lexical access, and the results showed that the inclusion of the lexical access leads to the exclusion of phonemic awareness. Further mediation analysis showed that, in fact, the lexical access mediates the contribution of phonemic awareness on number transcoding. Here just the regression models. To analyze our second research question, we conducted the regression analysis, and the results showed a dissociation between the cognitive mechanisms associated with lexical and syntactic and combined errors. So lexical errors were better predicted for phonemic awareness and lexical access, while syntactic and combined errors were better predicted for visuospatial and phonemic awareness. Just the regression models. So, in conclusion, we found that lexical access is a significant predictor of number transcoding, and that, in fact, lexical access mediates the contribution of phonemic awareness in number transcoding. This finding highlights that general cognitive mechanisms might be also important to number transcoding. We also found that the error types were differently associated with the phonological processing components, which is in line with our expectations. And this find supports our hypothesis that these cognitive mechanisms would be important for different steps of the number transcoding process. Lastly, we found that number writing, since phonemic awareness and lexical access are significant predictors of number writing, we found that number writing word spelling shares similar cognitive mechanisms, and this is especially important since it might explain the association between difficulties in reading, writing, and on math, so dyslexia and calculia. So that's all. Thank you for your attention.
Thank you, Malu. We also have time for maybe one question.
Yeah, I'll be glad to ask.
Yeah.
Thank you, Malu, because it was very interesting. I wonder, I know from neuropsychological studies that there are dissociations between number transcoding and even specifically the lexical errors and certain tasks, specific tasks of lexical access, like reading words or naming pictures. And I'm wondering, do you think maybe here you used the rapid naming as index of lexical access, right?
Right.
So I wonder, maybe do you think there could be something different about these different tasks that might explain why your task shows relation with the lexical errors, whereas other tasks of like picture naming show the dissociations?
Mm-hmm. But these studies are related to lexical errors in which type of task?
What we found in a neuropsychological study, in few case studies with the people who made lexical errors in reading or saying numbers, and then they did not make errors or such errors when saying pictures or saying or reading words, or they made different types of errors. There are few neuropsychological studies along this line. But I think that none of these studies, as far as I recall, used the rapid naming task that you used here.
Yes. Our task, in this study, we used number rapid naming task. But we also have a letter and a figure naming task, and at least with the letter rapid naming task, we found similar correlations. So I think that we would probably find a similar result.
Thank you.
Thank you.
Thank you, everyone. So I'll go next, and maybe at the end we can open for more questions. I will share my screen. Oh gosh. Okay. So I think you can all see my screen now.
Yeah.
Okay. Thank you. So thank you for being here. As I said, I'm Bella. This is a work I've done in collaboration with Malu Gomides, Professor Vito Halsey, and Professor Ed Hubbard when I was a PhD student at UW-Madison. And it's about fraction writing. It's called from 1/2 to 12. So probably I don't need to convince you guys that fractions are hard. If I ask you to solve these problems on the screens, how many possible fractions are between 1/8 and half, or to solve 4/6 split by 3/12, Maybe for you, this would be very easy, but for many children and adults, to get to the correct answers, it's challenging. We know that fractions are very hard. But fractions are also very important. Many studies, they show that fractions are the main predictors of algebraic knowledge, and that algebraic knowledge, they predict mainly several life outcomes, such as graduation rates, income. So by teaching fractions in a very good way, we can be helping people to succeed in the future, sorry. But as I mentioned, fractions are hard, and we don't really know the source of this. The figure is many people would say that we did not have a perceptual system to process fractions, and that maybe is the reason why learning fractions is hard. But our research team has recently shown that we can process non-symbolic fractions, that we do have a system that processes non-symbolic ratios. But also, when we look at symbolic fractions, they have a very hard structure, because the symbol for symbolic fractions, they represent at the same time different things, such as an operation, a proportion, a magnitude. So it can be hard to learn this new symbol. And also, when children are learning how to name fractions, they are acquiring a whole new vocabulary. So we have these different forms of representing fractions: non-symbolic, a visual form with Arabic digits, and a verbal form, and we can convert between them. So here in this study, I'll be focusing on how we convert between one notation to another, or how we transcode fractions, and I'll be particularly focusing on how we convert from the symbolic notations to one another. So we couldn't really find many studies that previously investigated how people transcode fractions in a systematic way. We found a study from Gelman and colleagues from 1989, where they investigated fraction reading, and they found that when children are reading fractions, they suppress or modify the vinculum. So when they are presented with a fraction in a visual format and they have to represent this fraction to a verbal format, they use weird notations. So for example, instead of saying 1/2, they could say 1/2. So reading the fractions as if it was 2 single digits, whole numbers. Reading the fractions as if the fraction was a whole number with 2 digits. So for example, reading 1/2 as 12, or reading the fraction as an operation, but in wrong operation. So for example, reading 1/2 as if it was 1 + 2. We also found a previous work investigating how children write fractions, so how they convert from the verbal notation to the visual notation. And they also found that children use weird notations. So for example, if they were writing the word 1/2, they could separate the numerator and the denominator by 1 space, so forming 2 single-digit whole numbers. They could instead split the numerator and the denominator with a comma, or they could split the numerator and the denominator with a dash. So difficulties with the vinculum, which is the bar that splits the numerator from the denominator. So all of these errors, they kind of resemble what we know as the whole number bias. So the whole number bias is when we apply previous knowledge from whole numbers to fractions. And it seems that children, when reading and writing fractions, they were actually processing these fractions as whole numbers. So producing whole numbers in this transcoding task. But we couldn't, as I mentioned, find a lot of studies that investigated this systematically. So our research question here was, how do people who are still learning about fractions write common fractions? We were not only interested in accuracy, but mainly in the error types that people make. So that's why we focused on people who are still learning fractions, so we could see the type of errors they commit. To investigate this, we recruited Brazilian participants, and we focused on 2 different groups. So we focused on adults who had low literacy, so adults who could not go to schools when they were young. So they had a lot of familiarity with fractions in their daily lives, but they have no formal instruction to fractions. We had 20 of these participants. They were from an adult education program. They were in the 1st and 2nd year of this adult education program. Here I'll be calling them, I will be referring to them as AEP. And we also had 20 children who had not so much familiarity with fractions, but who were already learning some fractions in schools, but not in a systematic form, since in Brazil, fraction instructions, they are mainly focused off the curriculum in 3rd and 4th grade. So all participants, they completed a fraction writing task. So we presented them with a fraction in the verbal format, and they had to convert to a visual format. So for example, if we said 1/2, they had to write that using Arabic digits and using the vinculum or this bar. In total, participants completed 27 items. We selected 27 single-digit irreducible fractions. We wanted to use irreducible fractions to avoid any problem when we were analyzing the items. We didn't want to be confused if the participants got the incorrect result, or if they understood the fraction, wrote the right fraction, then reduced the fraction. So we used irreducible items. And just before I show the results, I just want to say that how we name fractions in Brazilian Portuguese. So it's very similar to English. We use for the numerator the same words as we use for whole numbers. And for the denominator, we use the same words as we use for ordinal numbers. And then when the numerator is larger than 1, we include an S to indicate plural at the end of the ordinal number. And we have few special cases. So for example, for half, we have a special word. And for thirds, we have for 3, when 3 is the denominator, we also have a special word. But in general, it's very similar to English. Participants also did control tasks. They completed intelligence tasks. This was particularly important for the AP participants because we wanted to understand if they were they had low literacy due to intelligence reasons, or if it was more due to life opportunities. And participants also completed a whole number writing task. I will not be focusing on this today, but participants had an average performance. So we did not have participants with very low intelligence. So showing first the results with the data from the adults, the average performance in the task was 0.6. So they got about 60% of the items correct. We actually had an interesting case where about half of the participants, they knew how to write fractions. So they had a good performance in the task, and about half of the participants had a very low score in the task. And then here I'll show you the percentage of correct for each item. So here on the x-axis, we have the item of the task, and the y-axis, the percentage. And overall, I was expecting to see maybe a ceiling effect for half, but this didn't happen. So all the fractions, they were kind of similarly difficult for all participants in general, for most participants. As I mentioned before, we were more interested in the type of errors participants committed. So we classified the errors inspired by the whole number literature as syntactic, lexical, combined errors, or other when the errors did not apply to any of this. For the syntactic errors, we understood this when participants changed the format of the number. So instead of writing the fraction as a numerator and then the vinculum and then the denominator, when they wrote a different format. For lexical errors, when they kept the format of the number but used wrong digits, combined when they did both. And then other was when participants left the item blank or they wrote something that was not a number, for example. So overall, what we saw is that participants committed mostly syntactic errors. Few participants also committed lexical errors. Combined errors, they were rare. And so I'm going to show a few examples, the examples that were more frequent for each of these categories. So for syntactic errors, many participants wrote fractions as if it was a whole number composed with 2 digits. So for example, 1/3, they would write this as 13. This corresponded to 25% of the total errors. Many participants also wrote the fractions as ordinal numbers. So they would hear 1/8 and then write that as 18. This corresponded to 19% of the total errors. And also participants sometimes wrote the fractions as first a whole number is split with a space and then an ordinal number. So for example, 5/8, they would write 5 and then 8. And then few participants wrote the fractions as 2 ordinal numbers. So for example, they would hear 2/5 and then write 2nd, 5th. For lexical errors, we observed when they kept the fraction format and kept the numerator correct, but used a different digit for the denominator, or the opposite, when they kept the fraction format, used the correct denominator, but a wrong digit for the numerator. And then, as I mentioned, few participants, they knew how to write fractions. Few participants, they didn't know how to write fractions. So we split participants according to the most frequent error they committed. And we found that among the participants, about 14 of them committed mostly lexical errors, and 13 of them committed mostly syntactic errors. And then we compared their scores, and we noticed that participants who committed mostly the lexical errors, they were the ones who did very well on the task. So they had accuracy almost like of 100%. They did very well in the task. And participants who committed mostly syntactic errors were the ones who were struggling with the task. And so now I'll quickly go through the results of second graders. We would expect that second graders would do well in few items, but actually we saw a floor effect in the task. Participants couldn't write even half. And so this was surprising because we would expect the more familiar fractions they would know. And most participants committed syntactic errors. Nobody committed lexical errors. So these are examples, and the type of errors children committed, they were very similar to the type of errors the adults committed. So they would write fractions as a whole number composed of 2 digits, ordinal numbers, whole numbers and ordinal numbers, or 2 different single-digit whole numbers. So in general, what I saw is that people who are still learning about fractions, they may struggle with fraction writing. Many people may guess that because they know how to write whole numbers, they may learn very fast how to write fractions, but this seems not to be the case. It seems that writing fractions can also be challenging. And we also observed that participants who struggle in the fraction writing task, they made more syntactic than lexical errors, and the opposite profile, participants with better scores in the fraction writing task, they made more lexical errors. And finally, we saw that for the syntactic errors, the most frequent type was to write fractions as whole numbers, which we have seen before in the literature, but also write fractions as ordinal numbers, which was new for us. We kind of based on this, we thought about a developmental model. We believe that previous knowledge participants have about numbers in general, particular whole numbers, ordinal numbers, they may help them writing fractions. But when they are still learning how to write fractions, they have poor fraction skills, they may commit a high frequency of syntactic errors. Then as they start a transitioning phase and they start learning how to write fractions, they may still commit few lexical errors, maybe due to disattention, or to hold the numerator and then the denominator in the working memory and then writing this using the bar. So maybe we would have here some role of executive functions and maybe phonological phonemic awareness, which we have not investigated in this study. They may be the cause that people still eventually commit few lexical errors. And then when they master fractions, the errors are very rare, almost inexistent. And all of this may be impacted by formal and informal experiences with fractions, since here we saw that even adults with low literacy who have not learned fractions in schools, and about half of them could still write fractions correctly. So informal experiences may also contribute to fraction writing knowledge. So that's it. We would love to investigate this model. We still have not done that. I would like to thank Ed Hubbard, Malu Gomides, Vitor Hazi, who are my co-authors, and also the funding agencies. And that's it. Thank you. I don't know if we still have time for questions. Okay, I think maybe Júlia could start, and if we have time at the end, we will open for questions.
Thank you, Bella. I'm trying to share my screen. I'm not sure if it's in the presentation mode. Did it work right? No?
We see it, but not in presentation mode.
Okay, I think it's working now, right?
Yeah.
Yes.
Yeah. Okay, thank you. I am delighted to discuss these 3 talks. So in my presentation, I thought about briefly, very briefly, summarizing main aspects that the 3 colleagues mentioned, and also try to think about directions for future studies and challenges that we still need to face when studying number transcoding. But before, I just want to briefly emphasize how important it is that the child learns to write numbers. Even though it might seem a very easy task, it is an important predictor of future math skills. Longitudinally, we have data in the literature showing that the ability of a kindergarten to write and read and also to identify numbers is very important to arithmetic skills further on. And also that just the analysis of accuracy of a simple number writing task can be a strategy to identify children with math learning difficulties, especially in the early elementary school. So it is a very relevant and hot topic in numerical cognition. And even though for us adults, it's quite simple, for children, it imposes a very load of difficulty. And we can see that when we analyze the errors. So I think that that's something that we saw both in Malu's and Bella's talk, that the error analysis is an important source of evidence that we can try to understand the underlying mechanisms through which children learn number writing and fraction writing. So, and what I think is interesting when I saw the presentation of the colleagues, it reminded me of Julia's taxonomy of the influence of linguistic influences in place value. And when they published that paper in 2018, she focused on the fact that many transcoding papers were assessing the lexical influences, so the influence of inversion words, for example, in number writing. And I believe that from the 3 talks that we saw today, we can also think that now we have some work on the visual spatial orthographic, on place identification, not transcoding errors, but on number writing from Dotan's presentation. And also Malu showed the impact of phonological influences in place identification. So it's interesting to see that over the last 4 years, we have some new field of linguistic investigation in place identification. And now I'm gonna go through each of them. It's in a different order. I'm sorry, I thought that Malu was going to be the first one to present. So first I'm going to briefly discuss the challenges and the surprising findings of Malu, then of Dror, and then of Bella's. So first, phonological processing. It's I think it's very nice that Malu builds up on our previous data from the lab that phoneme elision also matters to number transcoding. I think that we all agree, and the 3 previous presentations mentioned that phonological working memory has been quite consistently discussed in the literature as a cognitive mechanism that impacts number transcoding. But we have been arguing that based on the ADAPT model in the first step of phonological encoding, phoneme elision might also be an important aspect. And I believe that Malu adds up a new source of evidence by emphasizing the role of lexical access by means of rapid automatized naming task. And that's interesting because when it comes to word reading, word writing, and dyslexia research, it has been argued that lexical access by means of a rapid automatized naming task, it's an important predictor of word reading and writing, and especially in more transparent languages, such as Portuguese. We are not as transparent as German, but we are not as irregular as English. So Cláudia Cardoso Martins, for instance, emphasizes that in Portuguese, rapid automatized naming tests, they are an important predictor of word reading and writing. And it's interesting to see that it also holds for number reading and number writing. And Another surprising finding that Malu shows is the role of visual-spatial working memory in number transcoding. So differently from the phonological working memory, which I believe it's more consensual, the visual-spatial working memory is less clear, and especially I think we need to think about the underlying mechanism through which visual-spatial working memory might impact number writing, I'm sorry. And maybe it's associated to the place value understanding when the child needs to create slots to be filled. But I think that future research is still needed in order to understand how visual-spatial working memory and if visual-spatial working memory is consistently related to number writing. And I think that at last another important point that it's related to Do's question to Malu is that it's always very hard to disentangle the specific role of task features. So I brought this image from this Cunningham paper that says that it's very hard to find a true phonemic awareness test, because we can classify phonological processing tests according to various features, such as if it requires a verbal response, the kind of information that needs to be manipulated, and especially in the case of the phonemic awareness that test that Malu was using, of course, there is a huge load of working memory. When we ask the child to suppress a phoneme, like cup without k, obviously it needs to hold and to manipulate the information working memory. So that's a challenge that is still hard to try to think of a phonemic awareness task that does not demand so many working memory abilities, and especially for children that already know how to read. Because for kindergartens, you can, for instance, try to deal with rhyme, but children in elementary schools, this task might be a bit too easy, so it's hard to disentangle the other components to try to think of a pure phonemic awareness task. So I think that in future studies, it will be important to try to think about experimental approaches to assess these phonological processing skills. I don't know, such as maybe phonological suppression somehow. Also, the phonological similarity between numbers is something that both Malu and Bella's presentation, we were, when I was reading their papers, it's something that it's hard because there are some number words that are quite similar and they might be more prone to errors associated to phonological processing. And it's important to also assess different age ranges because there are some work that suggested that the interplay between phonological processing and metacognition, it changes according to age and education, and also to have studies on dyslexic populations, because most studies with dyslexia, they focus more, most studies on dyslexia and metacognition, they focus more on multiplication and arithmetic word problems. But there are just a few. One of them is from Ricardo Moura, who is here, that analyzes how this population, who supposedly have problems in phonological processing, how they will write and the kind of errors they will make. And according, then moving to the next talk, I think that Dotan taps the Sapir Work hypothesis that the language that we speak shapes how we think. And I think it's particularly interesting, the fact that he shows that it's not just about the inversion. The inversion plays a role, but other linguistic characteristics, such as the writing habits, might impact differently the writing orders of units and digits. So it's important that when we're studying inversion, we take into account other linguistic features. He emphasizes the writing direction. There's also some work by Júlia that emphasizes the transparency of language. So comparing, for example, German and English, that's something that might interact with the inversion per se. Also, Dotan mentioned in his talk this interplay of syntax and also working memory, because it might be the case that the more syntactically complex numbers, they would require more working memory, and especially because usually the more syntactically complex numbers, they tend to have a higher number of syllables, so we might pose a cognitive overload in working memory. And but what I think it's, when I was reading his work, what I was thinking is that it's interesting, because when we think about the assumptions of the ADAPT model, that by second grade, the two-digit numbers should be already lexicalized, which means that they should be already automatically retrieved. It might not be true for every language. So even though he was not analyzing the errors, but the writing order, it's interesting that even adults, they might write it in a different way. And it's not that this means that they haven't lexicalized it, but that we should take inversion and other linguistic aspects, such as the French 80, that it might be that according to some specific linguistic features, second graders might not be able to lexicalize. And I think that future studies on that would benefit from using more fine-tuned measures, such as assessing the tracing dynamics and the pauses, because maybe someone did not invert, a German person, for example, did not write it in an inverted order, but it took longer to deal with that. Also, some eye tracking studies for number reading too. Also, this challenge to try to experimentally control for this interplay between syntax and working memory. And I think that assessing this in developmental studies, because we are probably going to have more errors, and also in groups with learning disabilities, we could also check if children that make more transcoding errors, they tend to write units first, for instance. And at last, I'm going to comment on Bella's talk on fractions, which I believe is quite relevant, because many studies on number transcoding work with whole numbers. So it's interesting to see that Bella proposed this developmental model. And I think it's especially relevant because she also analyzes the errors they make while writing. And error analysis, they are quite difficult to perform, but they are very rewarding, because I think we can learn a lot from them. And I believe it's interesting to see that the informal experiences, they play a role. So she investigated these adults with lower education. And when I was reading it, it got me thinking that it might be interesting to assess the role of home numeracy experiences, to see if children, for instance, whose parents engage more in home numeracy activities, they maybe have some informal experiences and they might be able to write something. And also the phonological similarity that I mentioned in Malu's presentation. And I think that it's also interesting to replicate this model in other languages, because it's funny, not funny is not the right adjective. It's interesting that they make these whole number errors, and that they make mostly syntactic errors when they are learning fractions. And maybe it's because in Portuguese, they do not encounter difficulties anymore while writing two-digit numbers. But maybe in other languages with inversion, for instance, it might be the case that other kind of errors can be more important when they're still learning fractions. And at last, to conclude, I think that a challenge we face, and that Dor mentioned in the end of his talk, is that we need to think of how to implement these findings in improve children's instruction, and especially by means of understanding how they learn it. I think it's important to plan interventions, but I think that understanding that the syntax is important, but there are some peculiarities, such as the 4-digit number in Arabic, for instance, and that understanding whether it's syntax or working memory or phonological processing might help us to plan interventions, and also to think that both formal and informal education play a role in number transcoding. So we saw that formal education reduces the unit decade writing order, and also reduces the number of errors children make, but the informal education plays a role in fractions. So having math both at schools and at home might be very helpful to help number transcoding in general. That's it. Maybe, sorry, it took me a little bit longer than I was supposed to, but I want to thank you for your attention. I had too many interesting things about the talks that I needed to approach. Thank you very much.
Thank you so much. And I also would like to thank everyone for being here. We are a little over the time, 10 minutes past. If people still want to hang out and talk about it, I'll be here. But yeah, thank you everyone. And thank you. I've learned a lot today.
Thanks.
Thank you.
Thank you.
Thank you, guys.
Shoot, it was cool.
Thank you, everyone. I really enjoyed it.
I wanted to ask you a question, Belle. Earlier you said there was no time, but do you have a minute?
Yeah.
Do you think that the difficulty, the errors they made when writing the fractions was like a thing of a conceptual thing that they just don't know it, or some form of cognitive development that has not yet been finalized?
Yes, I think
we have, I'm doing now the study on the number reading with children, and we ask ourselves this question all the time, like how to disentangle cognition from knowledge.
Yes, I think that to answer your question properly, we would need more data, and I would love to see the longitudinal curve. So to see children, because we only investigated second graders, so I would love to see third graders, first graders, and also when they start learning about fractions in schools, how this develops. Because if it's a conceptual thing, maybe when they start learning the concepts more formally in schools, we would see a shift in their error pattern or in their response accuracy. Where fortunately we could not collect this data when we started this. The pandemic happened. I was supposed to go back to schools here in Brazil, and they only opened this year. But I think maybe it could be both. I think it's still just an empirical question. We would need more data to answer.
Well, I was thinking it was super interesting that you can see the same sort of patterns as you see with like natural numbers, right? This thing where they just write down what they're hearing, like the natural number and then the ordinal number, which seems to be like indicated with an O in Portuguese.
Yeah. Like 1/8.
Yeah. So basically they just write down what they're hearing. That's it. So
yes,
whether that says that they don't know how to write it down, or whether they're just, whatever.
Yeah, it was very interesting because
I don't know, you showed the data of all things. I wonder if you looked at individual subjects, because what we try to do, for example, in our data is to look at single subjects, and then, well, if someone makes 100% errors, then obviously they don't know, but if they make around 50% errors, then it's not necessarily cognitive, but they definitely know something, right?
Yeah.
kind of more a little inclines towards the cognitive explanation.
Yeah, and Julia
Yes.
pointed out it would be super interesting to do the language comparison because in German,
Of course, it's different.
so the ordinal number is different from the denominator. So you say der vierte is like the fourth sort of item, but you say ein Viertel, which is so Viertel is the denominator and vierte is kind of the ordinal number. So that wouldn't be yeah, that these errors wouldn't be in German, I would say.
Oh, actually, it's the same in Hebrew too.
Oh, sorry, it seems that my Wi-Fi is bad, but for me, it was super interesting to see that they write what they hear, because people in the fraction literature, they've been talking a lot about the natural number bias or whole number bias, but nobody seems to be talking about ordinal numbers. And at least in Portuguese, it seems that ordinal numbers, they also interfere, at least in the beginning of this process of learning fractions. So maybe teachers should be focusing on ordinal numbers too as a source of interference. And yeah, people are not really talking about that.
Bella, I was curious when I was seeing like the different kind of syntactic errors you said. You said that like almost all of them said that they made syntactic errors, but I was curious because the kind of syntactic errors you mean is probably very different from what we mean, right? So yeah, I was curious to hear more about it.
Yes, I don't know if that's the right way of coding that, because we invented that, this type of classification. My idea was mostly that when they made this type of syntactic errors, they made a different number. So they changed the magnitude. Many times they created a 2 or 3 digit numbers. So yeah, the syntactic errors are definitely different. One thing also that I didn't show here that was very interesting for me is that many children, they inserted a lot of digits repeatedly. So for example, if it was 3/4, they would say 3 and then 4, 4, 4, 4, 4. Yeah, so very interesting. Okay, so Ed is saying that we could share the items, and then if you want to and have the chance to collect this data there with different in different languages, we could compare the data. And maybe if Júlia wants, we could also try to collect data from older Brazilian children, since the second graders had a flora.
I mean, we could also do it in English then, of course, right? So kind of see whether, because in English, the same thing should happen as in Portuguese, I think. So it's 1/4, right?
Yeah.
Or, well, that's the question, whether the same thing happens. And then it shouldn't happen in German. How is it in Arabic, Dror? So also like, is it?
The fractions? I think my knowledge in Arabic ends in the whole numbers. I understand that I made good impressions with my accent, probably not on the Arabic speakers, but maybe on the Latin language speakers. But I wanted to say, Júlia, about what you said to Bella earlier about the syntactic, whether the errors should count as syntactic or not, because it's really interesting. I think what it means, syntactic errors, and also in number transcoding, there's a whole bunch of errors that we call syntactic, and they don't always go together, right? I mean, some people do these or others, and it's more like a philosophical justification for why we call them syntactic. Never sure how much the justification is philosophical or cognitive.
Yeah, I agree. We always struggle here on how classifying the errors, and
we do. Maybe it's interesting to talk about that too. Also, because we have like our scheme for classifying errors, and I'm never sure 100% that it's the best way to classify them.
Yeah, you know,
especially in writing. Actually, in reading, I mean, I already saw that it works, that it gets to nice results. But in writing, we're just struggling with them now. I admit that I have no idea how to classify them properly. It's much more complex than in reading.
I'm not sure if I agree with you that maybe it's because I don't know, you have your model of number reading, so the reading errors for you, they're they are easier in a way, I find it harder for number reading, classifying the errors. Yeah. Not that I find number writing easy to classify, but I think that number reading is even more difficult, because I think that, I don't know, we see many errors of zero, that they insert zero. So, okay, we have additive composition, multiplicative composition, and Ricardo calls this wrong frame, when the number of zero does not match the magnitude. But for number reading, I find it harder. I struggle reading your papers, trying to think of an easier way to classify them, but I think it's harder.
Interesting. Glad to talk about this if you want. But,
yeah, I'll be happy to. And let me just ask you, I was curious about that specific thing of the 4-digit numbers in Arabic. Is it just for 4-digit numbers? And does it also happen in Hebrew or not?
Yeah, it's the same.
Interesting.
And we also saw this this idea of single chunk for 4-digit numbers. What I mentioned is we saw it in writing. We did this number writing with a tablet, that we saw different patterns for the 4-digit and 5-digit numbers. Look like the 4 digits are chunked. I think there are also other languages that do it this way, no? That have this,
I'm not aware of it.
I mean, we just have worked on the paper where we looked at the hundreds in Portuguese, which kind of seems to be a similar thing.
Yeah.
Where you also have for the hundreds, you don't say, well, there's Brazilian, like Portuguese speakers. But in essence, it's also not that you introduce the hundreds word explicitly for the hundreds. So it's within one chunk, but it's kind of a similar thing.
Yeah, you're right. You're right. Yeah, it's similar in a way. Yeah. The lack of this.
Now that you asked it, sorry.
No. I was just saying that it's similar because both lack the multiplicand, the 1,000 and the 100. Yeah, I haven't thought about it, Júlia. You're right.
Because now I think that in Hebrew is actually, in a way, it's dual. Because if you would ask a language teacher, they would say that what I described in Arabic, this is the way to say number in Hebrew. But you could also say the numbers the English way. It's not like fully correct, but people will definitely understand what you say, and people sometimes talk like that, and it's like considered as a lower level of language, but people would say it. So,
yeah, and that's interesting. Like that Czech paper, that in Czech they have both like the formal way to say it and the informal way. I think that's even more complicated for children when they're learning the number system, right?
Yeah, sure. Let's confuse them a little.
Actually, see now with the children, with these third-grade children, it's interesting because we see that some children, not all of them, but there is some small group of the children who learn the 5-digit numbers in Hebrew before they learn the 4-digit numbers. And we test only reading, not writing yet, because we did it on Zoom now in the Corona. But it's interesting to see that there's double dissociation between the 4 and the 5-digit numbers.
Love this very nice symposium.
Yeah.
Gonna move on.
It's an interesting topic, right?
Yeah.
You think so? Right. Okay.
Yeah. Nice seeing you all.
Yeah.
Okay.
See
you. You all, and yeah, I'll also be glad to talk, Ed, about your proposition about this fractions.
Yeah, sure.
Yeah, well, Bella has all the pieces, so I'm just in part because she said she may have missed part of that conversation. I was making sure that I jumped in and said, hey, we'd be happy to share and to put together this, cross-linguistic comparison could be really neat. So we're still trying to get the Portuguese paper out, and so we'd want to move to get that paper out and share in parallel, and then be able to sort of put together a bigger cross-linguistic comparison. So, but yeah, I think that could be a lot of fun. So
yeah, that would
let's keep talking about this. And for now, I think I'm gonna run because I have another meeting in 6 minutes. I will see all of you later.
Yeah, perfect.
Bye,
everyone.
Bye.
Bye.
Bye-bye.
I guess we're